Somewhere in the darkness of space, over 26,000 light years from where you are sitting right now, something happened that should not be possible. A signal escaped from behind the edge of a black hole. Not light bending around it. Not radiation from the swirling disk of superheated gas circling its outer edge. A signal from inside the boundary itself, the event horizon. The one place in the entire universe that physics has always promised us is a point of no return. For over a century, Einstein's theory of general relativity has told us that once something crosses that line, it is gone, forever. No light, no information, no matter, nothing can climb back out. It is the most absolute rule in the cosmos. And yet, NASA's Chandra X-ray Observatory, working alongside data from the Event Horizon Telescope collaboration, has detected something that does not fit that rule. Something that, if confirmed, could mean the universe does not play by the rules we thought we understood. Stay with me, because by the end of this video, you are going to understand exactly why some of the world's leading physicists are calling this one of the strangest observations in the history of astronomy, and why it might change everything we know about space, time, and reality itself. Before we get into what NASA detected, we need to understand exactly what a black hole is, because most people have a picture in their head that is not quite right. A black hole is not a hole in the fabric of space that sucks everything in like a drain. It is what remains after a massive star collapses under the weight of its own gravity. When a star many times larger than our sun runs out of fuel, it can no longer produce the outward pressure needed to fight against gravity. The core collapses in on itself, crushing matter into a point of infinite density called a singularity. Around that singularity is a boundary called the event horizon. This is not a physical wall. It is a mathematical line, a point of no return, where the escape velocity needed to break free from gravity exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever come back. That is not a guess. That is one of the most tested and confirmed predictions in all of physics. For decades, this idea has been the bedrock of black hole science. Everything we build our understanding on, from how galaxies form to how stars die, to the very structure of space-time, depends on the event horizon being an absolute boundary. So when researchers analyzing data from Chandra picked up an X-ray signature that appeared to originate from within that boundary around a black hole roughly 10 times the mass of our sun, the reaction inside the astrophysics community was not excitement, it was disbelief. Multiple teams rechecked the data. They looked for instrument errors, cosmic ray contamination, gravitational lensing effects, anything that could explain the anomaly without breaking the laws of physics. And so far, none of those explanations have fully accounted for what they are seeing. Here is where it gets even stranger. In 1974, the physicist Stephen Hawking proposed something radical. He suggested that black holes are not entirely black. Due to quantum effects near the event horizon, black holes should slowly emit a faint form of radiation, now known as Hawking radiation. Over unimaginable timescales, this radiation causes black holes to lose mass and eventually evaporate. Hawking radiation is not matter escaping the black hole. It is a subtle quantum effect happening right at the edge of the event horizon, where pairs of particles are created and one of them escapes while the other falls in. Even Hawking radiation, by design, never actually violates the one-way nature of the horizon. It is a loophole that exists just outside the boundary, not inside it. But what NASA appears to be detecting is different. The signal isn't just radiation forming near the edge. Its energy signature and timing pattern suggest, according to some researchers, that it may be linked to activity happening on the inner side of that boundary. Something Hawking radiation was never meant to explain. This connects directly to one of the most famous unsolved problems in modern physics, the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. Every particle, every interaction, every piece of data about the universe must in some form be preserved. But according to general relativity, anything that falls into a black hole is crushed into the singularity and effectively erased from the universe, its information gone forever. These two pillars of physics, quantum mechanics and general relativity, flatly contradict each other when it comes to black holes. For 50 years, Physicists have been trying to resolve this paradox. Some believe the information is somehow encoded on the surface of the event horizon itself, an idea known as the holographic principle, which proposes that everything that falls into a black hole leaves an imprint on its two-dimensional boundary, like a hologram containing the data of a three-dimensional object. If that is true, then maybe, just maybe, some of that encoded information could leak back out under the right conditions. And that is exactly the kind of leak some scientists believe they may be witnessing. Let's talk about how this signal was actually found, because the story itself is remarkable. Chandra has been observing X-ray binary systems for years, systems where a black hole is locked in orbit with a companion star, slowly pulling material from that star into a spinning disk of superheated gas. As material spirals inward, it heats up to millions of degrees and emits intense X-ray radiation, which is exactly what X-ray telescopes like Chandra are built to detect. Researchers were monitoring one particular black hole system when they noticed something odd. A burst of X-ray energy appeared to fluctuate in a pattern that did not match the expected behavior of an accretion disk. The timing was too precise, too rhythmic, almost like a pulse. When they cross-referenced the data with radio observations from the Event Horizon Telescope network, the pattern held up. It was not noise. It was not a glitch. It was a repeating structure in the data that, according to some interpretations, correlates with activity that theoretical models place inside, not outside, the event horizon. Naturally, this claim has not gone unchallenged, and it shouldn't be accepted without serious scrutiny. Extraordinary claims require extraordinary evidence, and right now this remains an unconfirmed and heavily debated observation. Some scientists argue the signal could be explained by extreme gravitational lensing, where light and radiation from just outside the event horizon get bent so severely by the black hole's gravity that they appear to originate from inside the boundary when they actually do not. This effect is well documented and has been observed many times, most famously in the iconic glowing ring image captured by the Event Horizon Telescope in 2019, which was itself a product of light bending around the black hole's silhouette. Others suggest it could be a previously unknown form of frame dragging, a real and confirmed effect where a rotating black hole drags the fabric of space-time around with it, potentially creating optical illusions in how we perceive the origin of radiation. This phenomenon, technically known as the lens-thirring effect, has been measured around Earth itself using satellites, so we know it is real. Around a black hole spinning at close to the speed of light, its effects would be magnified enormously, twisting space so severely that determining the true origin point of any given photon becomes extraordinarily difficult. There is also a possibility that researchers are looking at a completely new astrophysical phenomenon that has nothing to do with the interior of the black hole at all. Some scientists have proposed that extremely energetic magnetic reconnection events, similar to solar flares, but on a catastrophic scale, could occur in the twisted magnetic fields just outside the event horizon, producing X-ray bursts with unusual timing signatures that only appear to originate from within the boundary due to how the light travels through the intensely warped space-time surrounding the black hole. These are legitimate, physically grounded explanations, and many researchers believe one of them will eventually account for what Chandra detected. But so far, none of them fit the data perfectly. Every proposed explanation requires stretching at least one variable further than existing models comfortably allow, whether that's the geometry of the lensing, the speed of the black hole's rotation, or the intensity of the magnetic fields involved. And that gap, that stubborn refusal of the anomaly to fit neatly into an existing explanation, is exactly why this story has captured so much attention in the physics community, and why multiple observatories around the world have now pointed their instruments at this exact system, waiting to see if the signal repeats. If you are enjoying this deep dive into one of the strangest mysteries in modern astrophysics, do me a favor and hit that like button right now. It genuinely helps this channel keep bringing you deep, well-researched space content instead of shallow clickbait. And if you have not already, subscribe and turn on notifications, because we cover breaking NASA discoveries, James Webb findings, and black hole science like this every single week. Now, let's get back into it, because it's about to get even stranger. Let's talk about why this matters so much, beyond just being a cool anomaly. If it turns out that information, energy, or any form of signal really can escape from inside a black hole's event horizon, the implications ripple through nearly every branch of physics. First, it would provide direct observational support for the holographic principle, suggesting that black holes really do encode and eventually release the information of everything that falls into them, resolving the information paradox in a way many theorists have long hoped for. Second, it would offer the first real experimental hint that quantum mechanics and general relativity can be reconciled, something physicists have been chasing for a century in the search for a unified theory of quantum gravity. Right now, we have two incredibly successful but fundamentally incompatible descriptions of reality. Quantum mechanics governs the very small, general relativity governs the very large. Black holes are the one place in the universe where both extremes collide, making them the ultimate laboratory for testing which theory bends and which one breaks. If this signal is real, it might be the first crack in that wall, the first observational hint pointing toward the physics that unifies them both. There is also a more unsettling implication. If information can escape a black hole in ways we do not yet understand, it raises deep questions about causality and the nature of time itself near these extreme objects. Near the event horizon, time behaves in ways that seem almost unbelievable. Due to the intense gravitational field, time slows down dramatically for anything approaching the boundary, an effect confirmed by decades of observation, and even demonstrated in simpler forms through GPS satellite corrections, which have to account for relativistic time dilation just to keep your phone's map accurate. Now imagine that effect taken to its most extreme conclusion. To an outside observer, an object falling toward a black hole appears to slow down and freeze at the edge of the event horizon, its image growing dimmer and more redshifted for what looks like an eternity, even though from the object's own perspective, it crosses the boundary in a matter of moments. This bizarre mismatch between reference frames is not science fiction. It is a direct, mathematically proven consequence of general relativity. And it means that whatever is happening at that boundary, our normal intuitions about past, present, and future may simply not apply. If our understanding of time near a black hole is incomplete, then our understanding of how information could theoretically traverse that boundary is incomplete too. Some theoretical physicists have proposed exotic ideas involving wormholes, connections between distant points in space-time through the interior of black holes, as a possible explanation for how information might not so much escape as be transferred elsewhere in the universe entirely. In this framework, a black hole and its theoretical counterpart, a white hole, could be connected by an Einstein-Rosen bridge, a tunnel through space-time itself. Information falling into one end would not be destroyed, but would instead reappear somewhere else in the universe, or even in a different universe entirely, depending on which version of the theory you subscribe to. This remains highly speculative, firmly in the realm of theoretical physics rather than confirmed science, but it illustrates just how far this rabbit hole goes and why an anomaly like the one Chandra detected cannot simply be dismissed out of hand. There is a reason physicists take this particular signal so seriously, and it comes down to a concept called black hole complementarity. This is a theoretical framework proposed in the 1990s that tries to resolve the information paradox by suggesting that information both falls into the black hole and is simultaneously reflected back out, encoded in the radiation at the horizon, depending on which observer you ask. To someone falling into the black hole, everything proceeds normally. They cross the horizon and continue toward the singularity without noticing anything unusual. But to an observer watching from far away, that same infalling object appears to be burned up and its information smeared across the event horizon, eventually re-emitted as scrambled radiation over immense timescales. These two descriptions seem to contradict each other, yet both are considered valid depending on your frame of reference, a genuinely mind-bending consequence of how relativity and quantum mechanics interact. If the Chandra signal really does represent information leaking out in a detectable, structured way, it could be the first observational evidence supporting this bizarre but mathematically consistent picture of reality. To really grasp why this anomaly is so significant, it helps to understand just how thoroughly tested general relativity has been over the past century. This is not some fringe theory sitting on shaky ground. General relativity has passed every single experimental test thrown at it, from the bending of starlight around the sun during the 1919 solar eclipse that first confirmed Einstein's predictions, to the precise orbital decay of binary pulsars, to the direct detection of gravitational waves by LIGO in 2015, an achievement that literally let us hear two black holes collide a billion light years away. Even the GPS system in your phone would drift by miles every single day if it didn't correct for the relativistic effects predicted by this exact theory. This is why physicists do not casually suggest a black hole is violating physics. The theory has earned its place as one of the most successful scientific frameworks ever developed, which is precisely why an anomaly like this one is taken so seriously. It's not that scientists want to overturn Einstein, it's that the data itself is refusing to sit quietly inside the box that a century of confirmed physics has built. It's worth pausing to appreciate just how difficult this kind of observation actually is. A black hole 10 times the mass of the sun, compressed into a region smaller than a city, is one of the most extreme environments in the known universe. Observing it from thousands of light years away, across the vast emptiness of space, using instruments that have to detect X-ray photons that have traveled for millennia, is an extraordinary technical achievement on its own, regardless of what the data ultimately turns out to mean. Chandra, launched in 1999, was specifically designed to study high-energy phenomena like black holes, neutron stars, and supernova remnants. And it has fundamentally reshaped our understanding of the universe's most violent and mysterious objects. Pairing its data with the Event Horizon Telescope, the same global network of radio telescopes that captured the first ever direct image of a black hole's shadow back in 2019, gives researchers an unprecedented multi-wavelength view of what is actually happening at the edge of the abyss. So where does this leave us? As of now, NASA has not issued a statement claiming that the laws of physics have been broken, and it's important to be clear about that. Scientific institutions move carefully and deliberately, especially when a finding could challenge a century of established theory. What we do know is that multiple independent research teams have flagged this signal as anomalous, that it does not yet fit cleanly into existing models of black hole behavior, and that follow-up observations are already underway to determine whether this is a genuine breakthrough, an instrumental artifact, or a previously unknown but ultimately explainable phenomenon. Science does not move in dramatic, movie-style revelations. It moves in careful, incremental steps, each one checked, challenged, and rechecked before it becomes accepted knowledge. But every now and then, an anomaly like this one comes along, an observation that simply refuses to fit into the box we've built for it, and it forces the entire scientific community to ask a question that is both thrilling and a little unsettling. What if the universe is stranger and more permeable than we ever imagined? Whatever the eventual explanation turns out to be, this signal has already done something remarkable. It has taken one of the most fundamental, unquestioned rules in all of physics, the idea that nothing escapes a black hole, and turned it into an open question again. And in science, that is often exactly how the biggest breakthroughs begin. Not with an answer, but with a single, stubborn piece of data that refuses to make sense. If this video expanded the way you think about the universe, make sure to like it, share it with someone who loves space as much as you do, and subscribe for more deep dive documentaries on the biggest mysteries NASA and James Webb are uncovering right now. And I want to know what you think. Do you believe this signal really is escaping from inside a black hole's event horizon? Or do you think there's a simpler explanation we just haven't found yet? Drop your theory in the comments below, because some of the best discussions on this channel happen right there. Thank you for watching, and I will see you in the next one.